should not happen, right? Hey, चलाइए आप. अब क्या करें आप बताइए. We can just join from a normal laptop and put the mic next to it because the mic seems to be working. Yeah. Huh. Yeah. Yeah. We can do it one at a time, but it's not working. Huh? जल्दी कर.
Hello.
Hi, can you hear me?
Hello.
Hi. Can you hear me?
So Balaji, can you speak?
I am speaking. Can you hear me?
जो काम चलेगा. I'll tell you what we do. Everybody goes on the laptop. We just say them on laptop. We give everybody a laptop.
Hello? 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 Can you hear me? Hello? Hello?
Hello. Hello. Check. Hello.
Can you just make it up the view? क्या बोलूँ मुझे is the oh, join us by so how do we do this? Can everybody join in now? Everybody have to be themselves mute. हो रहा है सर
Hi, Balaji. Can you hear us? Ronnie, can you hear us?
Yeah, I can hear you.
We can hear you as well. Very good.
Very
Excellent.
good.
Now we just need to get Balaji back on. I don't see him here. Does anybody know where he is? Right.
The second wave, where 10 years later, where it was the first time we were building data centers, which means we wanted to converge three different kinds of local area networks, one for Ethernet communication, and that is LAN, local area, and then storage area and high performance computing. And they were all LANs are Ethernet, SANs are fiber channel, and HPC was InfiniBand. And the convergence of these things led to a network on top of Ethernet, as always in these cases, which had to be simultaneously providing very low latency and high bandwidth and be highly scalable. Now, clearly, this is a success, but built into that requirement of building such a network was an assumption, okay, and it slowly became a dogma, which is that the only way to build this kind of network is to have the network signal congestion. So we have to have a new breed of switches and protocols. And I'm one of the people that believed in this dogma and I propagated it. Okay, what that means is around 2005, I joined a startup called Numova Systems. We built this Nexus 5000 switch. I am the switch and line card architect for it. And that was Cisco's first 10 gigabit per second Ethernet switch, or not the very first, but amongst the first. And then I also helped standardize new transport protocols like QCN, quantized condition notification, which is now used widely in LLM networks as DCQCN, that's a layer 3 version. And also, I helped develop DCTCP, which is now used Meta in the back end of Meta and LinkedIn. Okay, and these switches and these protocols are fancy, meaning there's a lot of signaling that is different, and the network signal congestion, detect and signal. And unfortunately, by 2010, this belief or this dogma got a reality check in that virtualization came in. So people began to use VMs, VMware, notably ushered in the virtualization era, and cloud computing became a thing. Namely, people were okay with sharing infrastructure with other companies. This wasn't very, obviously a success at the very beginning. But, like people were okay sharing their car, Uber and other things took off. People are sharing their homes, like Airbnb took off. So sharing actually became a thing worldwide in different ways. And so virtualization and cloud computing took off. Here, a good network is one that is available everywhere, and it also minimizes the friction for deploying new services. So cloud native companies like Uber, Airbnb, Spotify, all these guys, Netflix, they didn't ever have a network other than in the cloud, and they're happily running even now and very profitable. So this was sort of the big goal. But what happened was this migration to the cloud meant that you cannot now have access to fancy networks or protocols. You're inside these bubbles called virtual machines, and the operator doesn't give you access to the network elements. Okay, so then if you were a cloud company, then you have to be okay with the best effort service that TCP plus Ethernet provides, or you stayed on premises. So financial exchanges, high performance computing, they never showed up on the cloud, onto the cloud. Okay, because they want much better than best effort service. Okay, so where do these financial exchanges and where are they? Where do they work even today? So this is a Marwa co-location facility of the New York Stock Exchange, and so these are all a row of cages, what they call racks or cages, and one of these could be one or more of these could be Goldman Sachs, and another one is Morgan Stanley, and all these trading firms, Barclays, and whoever is trading at the New York Stock Exchange. They're all here, and but there is a strong desire, starting, let's say, the 2012, 2015 timeframe, for these exchanges to move into the cloud. Okay, and the reason that this was not easy to do is that the cloud was not good enough to provide a key requirement needed for financial trading exchanges, namely to provide fair market access. Okay, so what does that mean? So here's an example of something that cannot be done in the conventional cloud. So I'll give you two requirements. The first one is this. It is necessary to execute transactions in the order in which they're submitted. So what does that mean? So first of all, this is the diagram of an exchange. So these circles are all the market participants. So as I said earlier, Goldman Sachs and Barclays and Hong Kong, HSBC, whoever, okay? And these are all trying to access the exchange, and they get into the exchange through these nodes, which are the great gateways, okay? These squares. There's 10 gateways and 3 market participant nodes per gateway. And where they're going to try and submit their orders to and where it's going to process is this matching engine. Okay, so orders come from here to the matching engine. What is necessary is that even though this in the figure here, this looks like this market participant is closer to the matching engine than that market participant. In the figure, at least, it looks like this wire is longer. It is necessary that if this market participant submit an order first, then that it gets processed before a subsequent order placed by this guy. Okay, so it's first come, first served strictly. Okay, and so exchanges go to great lengths to design these networks to make all the wire lengths exactly equal. A few years ago, we got a tour of Singapore Exchange, and they showed us that the floors of the exchange are transparent, the electronic exchange, and they showed the wires are all the same length to the market participants. Okay, so great pains are taken to build fair exchanges. It's very hard to do this in the cloud because you're some virtual machine in the cloud, and there's another virtual machine, and these lengths are not easy to make equal. Okay, so I just said everything in this slide in words. Second one is what happens is when the market data is published by the matching engine, this is the data that quotes the price of a stock, or it releases what's called the limit order book. And the market participants all need to get that information simultaneously. So nobody can get it slightly ahead of somebody else. And that's done in these exchanges, this bespoke on-premises exchanges using multicasting. This is not easy to do in the cloud either. Okay. So here are 2 things that cannot be done in the cloud, but that it's necessary for an exchange to have if it was to move there. Yeah, so far so good. I hope. If there are any questions, please raise your hand, or I can answer them. Okay. So what happened was, I'm just explaining a couple of problems, right, that cannot be addressed in the cloud. So our research program around 2016 was the Self-Programming Networks research program, and there's a whole bunch of students and faculty colleagues. Mendel is at the university where I am, Stanford. He's operating systems, virtual machines sort of expert. He's a co-founder of VMware, in fact. And Amin Wadat is at Google, Mohammad Ali Zadeh is at MIT, and Anirudh Shivaraman is at NYU, and all the others are PhD students. And we tried to build systems and networks purely using software so that you don't have to touch the network, hardware elements, or upgrade them in any way. And everything works from purely the edge. Okay, so far so good. So we're trying to build high-performance networks without the help of the network. Okay, and how is that possible? Well, the secret sauce was we were able to come up with a clock sync algorithm and protocol. So this is the thesis of Elon Geng, one half of it. And we could do this with great accuracy on the public networks or purely in software at any rate, okay? And this allowed us, because we have this highly accurate clock sync, I'll show you how it allows us to enable financial exchanges in the cloud. I'll give you how that works. But it also helps us build, transform plain old TCP plus Ethernet and RoCE. RoCE stands for RDMA, or Converged Ethernet. This is what's used for LLM training. It allowed us to do exchanges in the cloud and transform these best effort networks into high performance, meaning that you could run these networks at near zero packet loss and delays at full utilization. And this is, as you know, not possible with TCP and Ethernet. You'll start losing packets and delays will be very high the moment you load conventional TCP Ethernet type networks at even 50%. Okay? So how is this possible? How can we take accurate clocks? How does accurate clock enable all this? Well, that's what I'm going to tell you in the rest of the talk. Okay. So here is the solution to the first of the problems. Keep in mind, I'm trying to get all the orders submitted here processed in the order in which they're submitted. Okay. So imagine that we were able to timestamp all the orders as they hit the gateway. Okay. So all the gateway clocks are highly synchronized. So now, when an order is placed, it gets a timestamp, and then let's call this a time perimeter. And this time perimeter could be even here, if you like, at the very edge. And once the timestamp is taken, no matter when the order arrives at the matching engine, the timestamp is used to put it in the right order in the queue before execution. Okay. So of course you may have to hold things up a little bit, but not so long, meaning you just have to hold it enough to equalize wire length differences. Okay. So this allows you to have an exchange that is fair in one sense, in the sense of order processing. Okay. And the second way in which we can be fair is to make sure everybody gets the market orders simultaneously at the same time. So you can use the same time parameters, and you can do it either here or there. As I said, it doesn't matter. There's a parameter. And you timestamp an order when you're releasing it at the matching engine, and you hold it until a future time when you're sure all of the market participant, the endpoints of this time parameter, all of them have it, and then you release it. So for example, today, when public companies do their quarterly announcements, they do send journalists and institutions the data that they're going to release, and they're obliged legally not to open it until 8 a.m. or sometime. That's an example of a time perimeter where you send something to a whole bunch of people and oblige them not to open it, and there are mechanisms for dealing with that. But here we can do it just in this way technologically, and we can do it at close to hundreds of nanoseconds of precision. Okay, so this allows us to create time parameters. So you can see how clocks allows you to take conventional best effort network and make up for its deficiencies. Okay, so that's one thing. So I know we started late, but I know it's 9 p.m. plus your time. So I'm going to share a joke. I looked up jokes to share, on Zoom calls, and it has to do with what's the joke about financial traders. Okay, so there are jokes about lawyers, there are jokes about professors. What's the joke about financial traders? And so there was a young trader in New York. They made a huge killing on the market on a particular day. Their boss was very happy. They got $100,000 or so spot bonus. This actually happens. If you have a really good day, your boss can give you a spot bonus. And the young trader, let's say in the early 20s, they ran off to buy a fancy car. And the next morning, they drove the car to work. As they pulled up curbside outside their office to park, some truck veered off from its lane, brushed against the side of the car. The driver's side is on the left-hand side, brushed against the whole thing and left. And the trader was livid, and so they called the police, gave the license plate number, and said, prosecute that guy to the full extent of the law, and just absolutely livid. The police person who was taking these notes said that, it's true what they say about financial traders. All you guys care about is money. And he said, what do you mean? And he said, well, your left hand is missing from the elbow down, and you've said nothing about that yet. And then this trader says, what? Where's my Rolex? Okay. So unfortunately, this joke, when told on Zoom, I know it doesn't work because you guys are all muted. And I know you're laughing, there, but I can't hear it. Okay, there you go. Sandeep said he can. Let's move on. Okay, guys. So you see how an example of time parameters, okay, how this works. All right, let's move on. So let's do the second example. How can I convert standard Ethernet TCP to high performance? And so what's happening today? Okay, so as you all know, like my video coming to you or a file transfer we're making, the sender of that data is going to keep sending packets until some bottleneck link capacity is consumed, and an associated switch buffer overflows, dropping packets. Okay, this happens in best effort networks. At which point, the sender will know about this because sequence numbers go missing in acknowledgements, and they retransmit or sometimes even have to time out. And that's how it works. They back off. They send less when they find congestion happened, and they increase sending rate again. Now, with on-ramp, that's the name of the scheme that we came up with, one of the 3 papers I showed you earlier. And what that does is exactly in the same situation. First, synchronize the clocks to the sender and receiver very accurately, as I'm showing you, and start timestamping all the packets. So take a timestamp of the sender and the timestamp of the receiver. So send the data and keep taking timestamps. The first packet that you receive where the timestamp exceeds, so you keep calculating the so-called one-way delay, okay, which is the receive timestamp minus the transmit timestamp. That's the time that this packet spent in the network in the one-way direction of going from sender to receiver. If that one-way delay exceeds a threshold, where threshold equals propagation time plus a margin, then like this, you know that some congestion has happened. So you notice that I'm detecting congestion without the switch telling me about it. Okay, this is where I don't need network support because I have accurate clocks. Therefore, the receiver says, or the sender says, they can, once the one-way delay is known and is known to exceed the threshold by some amount, the sender will pause transmission for precisely the amount required to drain the queue, but not so long as to underflow the link. This is how this system can continue to deliver high throughput and low delays. Low delay because the only delay that you see is here. It's not overflowing anything, no drops in particular. Okay, so that's an example of something we can do, and I will show you the demonstration of this in the cloud. And so here we're creating what I'm going to call a buffer headroom. Okay, you could also go one step further and create a bandwidth headroom. And this idea is due to Kurbaitis and Weber. I heard this when I was a grad student or a postdoc from Frank Kelly. This goes back to the early to mid-90s, and I thought it was a clever idea. And they came up with it in a particular, at the switch. The idea is not difficult to apply at the edge, and that's what we did. So imagine that I'm a virtual machine or a node in a network, and I'm connected to a link that is supposed to give me 4 gigs of capacity. I create for myself what I'm going to call a ghost buffer, which is a buffer. It's just a counter. It increments, the counter increments by the amount of all the bytes arriving on the wire. Okay, the amount of data, the amount of traffic. Just count the bytes and increment it. And drain this queue or buffer at a steady rate of 3.8 gig. 3.8 is 95% of 4 gig. Okay, it's also called a virtual queue. It was called the virtual queue by Kurbaitis and Weber. Okay, so you can see what happens now. When the sender sends traffic and the link becomes 95% utilized or hits 3.8 gig of utilization, this will instantly fill up. So I've converted a rate estimation problem into a buffer size, problem, buffer build-up problem. So now I have a fake queue. The link is in fact not fully utilized yet, but it's heavily utilized. So I start signaling congestion from here to the receiver, to sender, holding that sender at no more than 3.8 gig. Okay, so it's a nice idea that allows you to have about in this case, 5% spare capacity, so that all traffic can just whiz through without even filling the buffer. An extension of this allows you to slice bandwidth and provide what we call quality of service. The reason all this is interesting is that this was done using switch. This was done originally at the switches, like the previous thing was done. The switches were signaling congestion. Even this bandwidth scarring or bandwidth slicing was done at the switches. So you had this thing called fair queuing or weighted round robin type algorithms at the switches. You can now do this at the edge. And here's how that works. So an extension of this, a receiver who is being sent data from, say, 3 senders or 3 sender groups, green, blue, and pink, can allocate to each of them a separate ghost buffer or whatever rate they choose to have, such that the sum of this is less than, of course, the line rate. And otherwise, someone's going to oversubscribe, okay? So you can see now the green will not be allowed to overflow or exceed more than half a gig of sending rate and so on. Okay, so you can see how this doesn't use clocks because here I'm underflowing the link. I'm not allowing congestion to build up, but I don't know that the bottleneck is at the edge. So if there was an internal bottleneck, and in fact the actual sending, the limit was 2 gig, even though this line is 4 gig, I will now have the one-way delay to tell me that the congestion is elsewhere. Okay, so one-way delay is present even here, and therefore clocks are present even here. But in the event that the bottleneck is not on the network but at the edge, here's how you can contain the source or slice the bandwidth. Okay, so that's 2 applications I've shown you of clocks dealing with fundamental problems that arise in networks, and this is the conventional CPU cloud type network. Okay, so Uber has been using this system. There's a startup called Clockwork, which Elon Gang and I and others are, involved with, and we're trying to build these things and commercialize it. And so Uber has trialed the system in their Oracle Cloud development zone, and it shows that over a 40-hour period, the clock synchronization quality on the median level is around tens of nanoseconds, and the 90th percentile is no more than 100 nanoseconds mostly, and it spikes up to 300 nanoseconds. This could be because of background traffic that we don't control. And the manner in which the clocks are synchronized involves probes being exchanged. I'll describe how that works in a bit. And that allows us to detect congestion automatically as well. Okay. And finally, the on-ramp and clock sync together allow us to, this is standard TCP behavior in the cloud, lots of delays, packet drops and retransmissions, and high utilization. And when you turn on this scheme that we have, is an augmentation of TCP. Huygens is the clock sync algorithm named after the Dutch physicist who observed clocks synchronized when they were on a wall through weak coupling. And this is the name we gave the algorithm, our algorithm. And then on-ramp, which I just described, brings down delays and drops are eliminated. Throughput is not changed. So at high throughput, you can have no drops and very low delays. I'm going to demonstrate this to you. Okay? So I'm going to the third part of this talk, okay, which is what are the problems and challenges in the AI networking world, and how does ClockSync help deal with it? Okay, so in the conventional cloud, everything is, cloud networks, like think of Amazon or Google or Oracle or Azure or any of IBM or any of the Ali Cloud, any of them. They're built on top of TCP and Ethernet. This is the great success story of the second half of the 20th century, network technology-wise. And operating link rates are small, like typically 4 to 16 gig, maybe 25, for the virtual machines. The actual physical links could be fatter, okay? And they provide best effort service, which means they'll start incurring high packet delays and drops when the link is utilized at more than 40 to 50% load, okay? Now, what happens here is what's called over provisioning, or let's throw money at the problem if you want better performance, provide more capacity, and that's been the way of coping with best effort, in practice. And it's okay to be best effort here because think of when you're ordering your car over Uber or booking a ticket on an airline. There's a human involved in the loop, and you have about 250 millisecond grace period to reply because a human won't detect that kind of lag, right? On the AI side, first of all, the technology, the layer 2 technology that is used is not Ethernet. It's RoCE, which is enhanced Ethernet version called RDMA over converged Ethernet. I can explain that acronym, but perhaps you can look it up. And in the interest of time, let me proceed. Or what's called InfiniBand. This came from high performance computing. And the operating line rates are much, much higher, very fat pipes. And it's required that these networks be providing best performance. What that means is you have to have near zero packet delays and drops. Certainly packet loss should be zero. And utilization should be at least 90%. Okay? So it's just too expensive to over provision. and humans are not involved in the loop. So therefore, you don't get this grace period. So this is a very different world. Moreover, there's even worse things to happen. This is simply, what I'm going to call table stakes. The workloads in a conventional cloud environment can be very heterogeneous and highly uncorrelated. Okay, when Uber tends to go, Spotify might not, and it's not really related. There are different tenants. Even within a tenant, there could be different things happening, and they're not really correlated. Here, everything is very correlated. Okay, it's lockstep. And moreover, so flows run in lockstep. So if one flow is slow, then that tends to slow the entire fleet. So not only do they go simultaneously, that is, their compute followed by communicate. That's what I mean by correlated. They are always doing that. But if one of them goes slow, that slows down everybody. Okay, that's not true here. Okay, not necessarily. So the one way to think of, if you haven't worked with these sort of networks on the right, I presume that most of you know what this looks like because we've been living in this world for a long time. This is new. So here's one way to think of it. Here are all the servers. These are all the servers with GPUs, and that's where processing is done for this LLM, like stochastic gradient descent type algorithms are run. And these GPU and servers are connected through some network of the Rocky/InfiniBand type. It's a layer of switches and interconnecting these servers. And what's happening is, I'm sure you've seen some courses where you use PyTorch. So if you have LLM training that you're running, you can use PyTorch or Megatron or one of these other job launching type packages or systems. And what will happen is that it'll emit, this PyTorch in this case will emit, it executes a program by emitting what are called collectives. Collective is a task assigned to a group of servers. So what that'll look like is a collective will have a width. It's the number of servers it needs, or GPUs it needs, right? And I'm going to also show a height. Height is the amount of time it needs, nominal minimum time it needs to execute in the best case scenario. So for example, here's an all reduced collective. All reduces are being farmed out. And so the height is the amount of time it takes if nothing was to impede it. And the width is number of resources it needs. So if you think of this, one way of thinking of this, what's going on is these collectors are being dropped. So it's like playing Tetris. You're getting blocks. They're going to be placed on these resources. Resources will chew them up, and so on. Okay, so that's a very good way of thinking about LLM training from an infrastructure perspective. It's a first cut, good approximation. Okay, now what? Well, what can go wrong is this. So there's an all-gather primitive running and some NIC flaps, meaning the NIC connecting the network interface card that connects this server to the network undergoes what's called flapping. Flapping is gets too hot, and it temporarily is unable to communicate to the other side, and then it has to go do some recovery protocol, and all that time is added. Is nothing is getting processed. So all of these GPUs are now held up because this guy can't go. So I'm going to call this an injury time, like in soccer or team sports. One player is down, the entire game stops, and you're just collecting injury time. Okay, this is red. And then things get set right and it goes. Another thing that can happen is that you can have contention or congestion in the fabric, and that can cause slowdowns, and everything is slowed down because of this so-called, lockstep nature running. So the entire job of building high-performance clusters in this world, everybody, is to just minimize the amount of red. Okay, that's pretty much what everybody's doing. So how does this red occur, and what can we do to eliminate it? How do clocks help here? And that's what I'm going to tell you the rest. So current approach in industry, again, is to take a network-centric approach, is to design high-performance hardware switches and NICs that use signaling protocols, which are like in-band network telemetry, or INT as it's called. This is how Broadcom, NVIDIA, pretty much all the vendors are doing this, right? But the hardware-centric approach has some crucial drawbacks in the sense that it requires all the nodes of everything to be running all the time. Okay, so if one NIC or one switch fails, then it stalls the entire fleet. Okay. And secondly, it creates what are called single vendor. So first is technological problem. Second is a marketplace sort of problem, meaning you can't have switches from one vendor and NICs from another typically, or you can't have two different switch providers providing you switches. It has to be pretty much one entity doing the whole thing. And that's not desirable for, you get lock-in and so on. Okay, so it's more of a business reason, but it's technical in the sense that interoperability could be a problem, but because standards are just being put out there, until standardization fully takes hold, you will have single vendor solutions. So the way we can solve this problem is we just take Ethernet and we can build through software, and I'm going to show you how, what do the problems look like, and it scales. So let me say what happens. So if you blow up a bunch of servers, and one of these servers looks like this. So this is, if you go back 2 slides and look at this figure, right? I'm showing you what happens if you just consider, let's say, 8 servers for illustration purposes, and what's the nature of the problem that occurs there. So the first server, when you blow it up, it'll look like this. It'll have 8 GPUs typically. Each GPU will have 2 NICs to which it's connected. 2 is typically the number. It could be 1 sometimes. 1 with twice the capacity. And there's also a CPU. This is where you log in and do everything, and that's the Ethernet. So it's connected to 2 different networks. The CPU is connected to what's called the front-end network as Ethernet, and the GPUs are connected to each other through the Rocky or InfiniBand type network. And when you run these primitives, a ring topology or a tree topology set up connecting the let's say this GPU to its counterpart GPUs over here, and communication takes place on these things. So he sends some data to this guy, and that guy does some updates and forwards it here, and that's how it goes. And that's one example of this could be an all reduced collective runs on this. Okay. So specifically now, let's focus on one edge of this. Let's say server 1 sending to server 2. So I've blown up both the servers. Each one has 8 GPUs. And let's look at a GPU message being emitted. This message that is emitted is through this package or this thing called NCCL, NVIDIA Communications Collective Library, or another form, Microsoft has its own Communications Collective Library. That's how messages are sent between GPUs in this world of AI networks. And this message, this software, it's a software widget, and we sit over there, okay? And this message is broken into what are called chunks. Chunks are assigned to what are called Q pairs. A Q pair is an association. This is a Q pair here is an association of a location in this GPU's memory to this GPU's memory. At the same time, it's also when the data gets packetized, it's given labels, network address labels, and becomes a path in the network. So it goes to the network interface card, and then is mapped to network paths, okay, and then arrives on the other side where it's reassembled and placed back directly into the memory. That's the DMA, RDMA, remote DMA. That's what happens. Directly data is pulled out from memory, chunked, packetized, shipped across, reassembled, placed back in memory. Okay. The point is there's no kernel in this world. Okay. And so what I've shown you here is network paths. I'm going to blow this network up, and that's where the switches come. Top of the rack switch connected to each other through 1 level of spine, maybe 2. And the fat tree, the ring looks like this. These Q pairs, let's say there are green and orange Q pairs. This orange to green connects the first server to the second to the third through some other Q pairs. The colors are changing because the labels are changing. Otherwise, and these labels, these Q pairs are mapped onto network paths. Okay, so I hope this is clear. I know I'm going through a lot of concepts, quick time, but I hope distributedly, independently, this is how server 1 talks to server 2 through some paths, purely based on their addresses, and 2 talks to 3, and so on. And that's the ring. Now, as data is flying around, you can see some links are not very contentious, and others are heavily contentious. Okay, so this is how do we know where it's contending? Because it's all happening distributedly. In fact, sometimes you don't even know how many other nodes are in the ring. You just told what to do, and you know who's your node I, you know who's I minus one and who's I plus one, and you just keep going. Okay. So, as I mentioned to you, these network interface cards to the top of the rack space, those links can fail because of high temperatures and dust. So there's a industry magazine called Semi or online thing magazine called Semi Analysis, and they're saying that even if each link can fail once in 5 years, that's the mean time to failure. When you have 100,000 GPUs, there's enough links that you'll have a failure pretty much once in 26 minutes. Okay, so this is under the 5-year failure assumption. The failures are more frequent or less frequent. You can see what the minutes look like. Now, this just means that when such a thing fails, you have to stop the job, go back to a previous checkpoint, recover everything, and continue. So you may end up spending more time recovering, restarting, than actually executing the job. Okay? So what we can do, because we're in software and at a higher level, we can actually find alternate paths, that is, route traffic through other NICs, ignore the NIC that's failed, but use its neighboring NICs. Okay, and then keep monitoring the path so you can recover when the failure, when the NIC stops flapping. And so to show you how this works, in one case, the first one, this is normal operation. There are 16, 8 times 2, 16 NICs. Each NIC can send 100 gigabits per second. So a server can put out a total of 1.6 terabits per second maximum. Under normal operation, it sends a 1.5 terabits per second. It's pretty high. And this is all healthy. Run 2, a NIC fails. When the NIC fails, it crashes the job that's running on it. And when the NIC is revived or when the NIC comes back, stops flapping, the job unfortunately is dead. Third case is when we have our solution running, we can fail over to adjacent NICs and run at a diminished capacity, still high, but diminished. And as soon as the NIC comes back, we can recover the full bandwidth. Okay, so this is a way of doing things in software that compensates for hardware unreliability. Okay, so that's sort of interesting and one step beyond not needing hardware. This is actually compensating for hardware. Okay, so second is, in the TCP world, I showed you how on-ramp and stuff deal with congestion. I'm going to show you how we can deal with contention here. Okay, so what is that? How does it work? So let's say there are the green and orange senders, and they're sending to distinctly different receivers. They don't even know each other's existence. And each of them is using 2 queue pairs, one light green and dark green in this case, and light orange and dark orange in this case. And they're mapped onto some paths. It happens that the dark queue pairs are clashing on this link from spine to top of the rack, and that's causing contention. So these two cannot run at full speed because they have to share this bandwidth. Because they can't run fast, the light green counterparts also can't run fast. Okay, so this is the problem. This is happening today, and there's various ways of doing this with hardware support. I'm going to show you how to do the software support on clock sync. So what you can do is to detect congestion using very accurately synchronized clocks. So the green sender observes the one-way delay on the light green path is small compared to the one-way delay of traffic going on the dark green path, because the packets in the dark green path are encountering the orange guys and getting queued and hitting congestion, whereas in the light green they're not. The orange guy does the same thing. He observes the light orange path is less congested. So what we can do is to move some traffic from the dark paths to the lighter paths, so you can uncongest the heavily, you don't make it zero, you use less. So the right way to think of this is between here and here, if there are resistors, voltage is dropped between, let's say, this sender and that receiver, and it can go on this path, that is this path, or this path. Just as current doesn't follow the path of least resistance, but does in fact go inversely proportional to the resistance. So also, you look at contention, and then traffic is allocated away from contentious paths to less contentious paths. Okay? All right, how does this work in practice? So when we run 2 jobs, the nickel primitives, all to all, and the first one doesn't get past 90%, it stops at 84%. You can already see that there are these are the one-way delays of the Q pairs corresponding to the first job. Some of them are very low delays and some of them are high delays. You could have improved this guy by moving some traffic from these paths to those paths. But here we chose to let the second job come on. Both of them are hurting each other and doing much worse than less than 50% of their possible capacity. So again, you can see some paths are very uncongested and some paths are heavily congested. So by moving traffic from these congested paths to uncongested paths, when the algorithm is turned on, we can improve throughput for both primitives and make the one-way delays, the variance go down as much as possible. Okay, so I hope that explains how this works. And dynamic load balancing is a network-centric approach that's used in Oracle Cloud by default. And you can see that it's not able to do as well in the same scenario as what we can do, because this is more proactive and not congestion sensitive, whereas this is congestion sensitive. Okay, so sensing helps. And similar thing was tried at Meta, 2 jobs, in this case an all reduce, a second all reduce, and you can see no contention in the first and contention in the second, with a variance in the one-way delays, which was remedied by moving bytes from here to here. Okay, so that's all the stuff I'm going to tell you on tech, 3 different cases where time-sensitive financial exchanges were built in the cloud using ClockSync. Congestion was removed in TCP Ethernets, giving high throughput and very low delays and drops. And AI networks are sped up as well. Okay, so I'm going to conclude the talk and say the most important takeaway is, remember, time heals all wounds, okay, as they said very wisely. And then you can build networks with high performance if you have accurate clocks, because what it does is it allows you to sense congestion purely from the edge. And then you can do many things. And this works in the conventional CPU cloud as well as the GPU cloud that's just coming in now. And it's important to consider not, very hard to co-design computer network, because you end up, making things brittle. Okay. So that concludes the presentation. According to normal time, I'm over time. So Sandeep, just, or Ronnie, just, can I show some demos or should we just call it quits?
Sandeep?
No, demos would be nice.
Yeah, it'll be brief so you can actually see these clocks. Okay, so can you see my browser now?
No.
Okay, let me reshare. Okay, so you should be able to see my browser.
Yeah.
Yeah.
So this is a technology that's available on the public cloud. So all the Stanford work is now baked into some hardware solutions. So you can go to Google Cloud, AWS, Azure, Microsoft Azure, Oracle Cloud, and spawn your own instances, as they call it. So I've just launched 120 virtual machines on 10 gig links in Google Cloud in 3 of their zones, West Coast, Central, and Belgium. Okay. And that's what this is. I launched it just as the talk started. And you can see here that the 120 virtual machines that I launched, I'm speaking from my house, so the Wi-Fi could be a little, if it gets clunky, I'm going to remove my video. Okay. So here are the 120 virtual machines. 40 in Europe West is in Belgium, 40 US East, and 40 in. So here's what the 40 virtual machines look like. We can tell, in addition to the ClockSync is good enough to tell that these 2 virtual machines are quite likely on the same physical server. And the reason we can say that is because they're both deriving time. These virtual machines are deriving time from the same source, namely the crystal on the physical server. And because we're synchronizing clocks very accurately, we observe that we're applying same controls to these virtual machines' clocks. Therefore, we're guessing that they're in the same physical server. This is very, very similar to if 3 people are going on a bus and the GPS, not GPS, well, GPS 1, but look at the accelerometer readings, right? And if they're sort of behaving the same way, meaning when the bus brakes or accelerates and it does the same sort of jolting, you can tell that they're in the same bus. It's very similar, okay? So now let's look at the clock accuracy. So these 40 virtual machines are blown up as shown here. Reference clock is in Belgium. There are local references in US East and US West. This is the clock accuracy is 250, 240, let's say, less than half a microsecond of accuracy across this large distances. And the clocks are being synchronized using this probe mesh. It's a very nice theoretical algorithm. I would have spent some time on it in a different presentation, but I encourage you to take a look at the paper. These nodes are exchanging probes with each other and using the probes, that the probes are carrying timestamp. 107 says, my time is blah to 114, and 114 says, my time, I received the probe at this time. And then they use those probe transmit and receive timestamps, and the links are bidirectional, to figure out what the offset in their clock times is. And then they combine that through a local and a global step to do this clock sync. Every node is talking to other nodes in this probe mesh and syncing clocks, including the reference. Okay, so I'm going to not tell you about the algorithm. Okay, but let's look at one-way delays. Because these probes are going on this network, I can also tell how long are probes taking to go from Belgium to US West. Well, you can see here 67 odd milliseconds, 67.3 milliseconds is down here, 67.5 is up there. So this is the minimum, green is minimum, median, and 90th percentile delays encountered by the probes. This is in the case where there's no load at all. Okay, so you can see more. Let me zoom out a bit. Okay, so now let me quickly apply load and show you how this detects congestion. You notice that I'm not even touching the network because it's running somewhere in the public cloud. I don't even know where these virtual machines are. So I applied 71% load on this network, which means each node will randomly ask for a file from one of its neighbors in this graph, and then keep itself busy 71% of the time. Okay, so when that load is when the database updates, you'll see that the delay jumps up. The probes get delayed because there's also just other traffic. They're using the same paths, and so this becomes a silent but sensor of congestion. Okay, so this is an example of how you can use very finely synchronized clocks to. And notice there's one-way delays, right? This is forward direction, this is the backward direction, and they're not the same. Historically, in networks, we've always measured delays round trip times because we haven't had synchronized clocks. So for the first time, we can do one-way delays. And this is the 90th percentile is significantly higher. It's higher by about 6 milliseconds. Okay, so now let's see if we can get rid of congestion. This is the on-ramp algorithm. I'm going to turn it on for Google Cloud. Okay, so let's just see if I can bring down the congestion. So the blue line should come down. This is 90th percentile. By the way, these two are 99th percentile and maximum. Okay, so now when the database updates, it should bring down the congestion. Or see, now congestion has come down because we have turned on this congestion management algorithm. Okay, so this is how we can do congestion management. And I also have something else to show you on bandwidth slicing. In the interest of time, I won't do it, but I just want to show you on Amazon. This is a single data center, single region. Here are 20 virtual machines. Wow, Wi-Fi is slow. Okay, I'm going to just remove my video, guys. Okay, sorry, okay, it's come up now. So again, 20 virtual machines. You can see here, 2 of them are on the same physical server, etc. And it's very similar. You can do, the clock sync accuracy this time, because they're all in the same region, is much, much better, right? Sub 100 nanoseconds for the 90th percentile. So this is how you can build, let's say, networks which give you high performance at in sort of otherwise best effort environments, okay, without the need for specialized hardware. So let me stop with that and take any questions you may have. As I said, time heals all wounds, etc. Okay. I remember, Damon Wishik, Sandeep, he is someone I'm, working on this. He said, when, timeliness is next to godliness. I agree with all that. So, okay, let me stop there.
We have some time for questions.
Sorry, all this time stamping, does that cause any overheads?
Yeah, so the probes themselves do cause overhead. It's about 0.5% or up no more than 2% of a core. And so for each node. And the extra effort of doing congestion management using these timestamps on top of what TCP already does, it's TCP at full load is about 12 to 13% overhead, and this causes an additional 3% overhead. On the LLM network, the software module, the plugin now doesn't take more than 2.5% overhead. So, in other words, it is because software, it is an overhead, but it's kept so small as to be just negligible, and the benefit it gives in the order of 20-30%, as you saw. The improvement in LLM was 69 gigabits per second going to 92, and also in Meta you got some 29% improvement or so. So that's the sort of benefit you can get. But the most important thing is you don't need to have specialized hardware, and which has its own issues. It generally it's finicky. It runs, people build good hardware, to be fair, right? But at the same time, you're running this and it's so hot, things get really hot. When you run a job for like 3 months, I've heard the data center just keeps getting hotter and hotter and hotter and hotter, and sometimes I heard in one case they had to wheel in ice to just, the cooling system isn't able to cope with the amount of heat being put out. They just bring in ice and melt it, just to, relieve uh, temperature.
The questions from the audience?
It's been a very long day.
No worries. So,
Somebody, go ahead.
no, just to say, I think it's an exciting thing, for networking. Like sometimes networking goes through a period of dormancy, but every new application that comes brings its own challenges. And I think the AI, if you're a young person looking to work on networks, this is a good time to jump in. And it's not just networks. You think of it as distributed systems. Don't it's you could do hardware, but also much action on the software stack side. So I encourage young people to consider.
Are there any interesting algorithmic issues that come up because of this?
I mean, most of what I'm showing you, like clock sync and condition control, I've just simplified the presentation of the algorithms quite vastly. Like this, you remember how this, this utility function based framing of what this distributed senders are doing. So let me just briefly put this slide back. So here, uh, there's utility function based way of framing what these guys are doing. And everything is right now distributed. But if you had to make the collective work together, or if you want to make multiple collectives coexist and work together, it's possible for you to give more bandwidth to one and less to the others. And that sort of thing is entirely algorithmic. And as I said, the clock sync thing is very algorithmic. Uh, and so um, at the end of the day, it's yeah, I would have happily given a different talk. But I wanted to just show the span of applicability of something like clock synchronization.
Okay, so shall we wrap it up, Sandeep? Okay, well, great. Yeah, thanks for a very interesting talk, and that closes the session. So I guess we'll upload remotely.
Thank you.
Thank you.
Thank you very much, Balaji.
Bye.
Bye.
in what you maybe a different